Today we're going to be talking about the trapezoid rectangle approximation method, and the objective is to be able to approximate area under the curve using trapezoids and the trapezoid rule given a function, graph, or table of values. First of all, we need to make sure we're familiar with the trapezoid and the area of a trapezoid. So here's a basic trapezoid. Of course, the bases are parallel to each other and the height is the distance from one base to the other. The area is 1/2 the height times the sum of the bases. And I have here an example so we can get started with working one out that has numbers. This particular trapezoid is a right trapezoid because the left side of it happens to be perpendicular to the bases. So really that left side becomes the height of the trapezoid. So if we're working with area formula, you would get that the area is 1/2 the height, in this case it's 4, times the sum of the bases, which is 5 plus 8, that's 13, and reducing this gives you a total of 26. Okay, and that's just finding the area of a trapezoid. But for the purposes of finding the area under a curve, what I'll do here is I'm going to go ahead and just draw a curve that's going to help us get a visual of what we're going to be doing. Keep in mind that as I'm drawing this, you are welcome to stop, replay at any time to make sure that you are understanding completely. So we have this curve, call it f of x, and instead of using rectangles, and I'll show you that what that would have been using a rectangle feature here. If I wanted to draw a rectangle, in the past I might have used a left or a right hand rectangle. I'm going to use a left one just to show you. I might draw a rectangle like this. Okay, and then I might draw a rectangle like this. Okay, and we would find those areas, of course, and then try to approximate it that way. We could do a right, we could do a left, a midpoint, and we could do more than just two. But for the purposes of this lesson, instead of using rectangles, what we're going to do is we're going to use trapezoids. And I'm going to try to show you exactly what's going to happen, because here's where students get confused. First of all, we're going to take this trapezoid, and instead of lining it up here where the bases, the traditional bases are the base of your trapezoid, we're going to do something more interesting than that. We're actually going to rotate it so that the height of the trapezoid is really the base. It really kind of serves as the base. So you see? And in this particular example, it fits even nicer than the rectangle did, if you recall. So you can see how that's a lot nicer than that rectangle. But what's important here is that this base, it's really the height. The height of the rectangle is the base. Now if you recall from from rectangle approximation methods that we've done in the past, the difference in the x's, we call that delta x. So this line right here that I'm about to draw, we normally call that line delta x. And so why that's important is because you need to start thinking of this area formula. If we're going to find the area of this trapezoid, you need to start thinking of this h not as an h, but more as a delta x, the difference between the two x's. So far our trapezoid formula is not going to be changed, but it's going to change the way we write it. So let's say we have 1/2, that's still true, but instead of the height, it would seem that the heights are 5 and 8. Those are really the bases. The height is the difference in the x's. So in this case, we're going to change h to delta x, because that's really what it is. Now the next thing that happens is the bases. Well, the bases are now given by the heights almost. Okay, there's one, and here's the other one. So it's not going to be quite perfect, but you can kind of get the visual there. So the bases, instead of calling those bases b1, b2, those bases are actually going to be given by the y values of the function. Okay, so for example here we might call this the point. call this x sub 0. Those of you taking physics, you'll remember that just means the initial. And then we call this one x sub 1. You'll notice these points become x sub 0, and I'm just going to use y sub 0. Okay, and in this case I would use x sub 1, comma, y sub 1. And so when I'm going to go ahead and go back to my formula, instead of thinking them as bases, we need to think of them as the y values. So for the area of this trapezoid, the first base is going to be given by y sub 0. So I would put y sub 0 plus the next y, which would be y sub 1. Okay, and I should have really made this approximately. Now that's just one trapezoid. Of course, we would have to draw another one to try to complete the area under the function. But I just wanted to give you an idea of how the traditional trapezoid sort of gets rotated on its side, and now the height of that trapezoid becomes kind of like the base. It's the delta x. So our formula is going to look a little bit different when we go through the process than what you're used to. And this is still 26. Nothing has changed. Still 26. It's just that we've rotated. It looks a little different. Okay, let's go to our next slide. So how do I use trapezoids to approximate the area under the curve? Well, we're going to go ahead and take a look at this to develop the trapezoid rule. Okay, and we're going to draw a few trapezoids, and then reminding you that the more trapezoids you have, the better the approximation. And of course, in the end, if you have an infinite number of trapezoids, you would have the true answer. Let's go ahead and draw a couple trapezoids so you can see what I mean. Well, actually, before that, I'm going to go ahead and label my axes. So we're going to draw our first trapezoid. We're going to start it at 0, but we're going to call this, instead of 0, we're just generically going to call it x sub 0. Then we're going to go to 1, and we're going to call that x sub 1. Then we're going to call 2 x sub 2, x sub 3, and x sub 4. So the corresponding y values, or the points then, of course, would be y sub 0, y sub 1, y sub 2, y sub 3, y sub 4. I'll go ahead and put those in. X sub 0, comma, y sub 0. I'm going to press pause just to save us some time while I fill these in. Okay, so you see I filled in all my points. Okay, and so now what I'm going to do is I'm going to go ahead and start drawing trapezoids so you can get a better visual of how that's going to work. Okay. So my first one goes from x sub 0, x sub 1, so here's my first trapezoid, and I'm going to just press pause on my recording and go ahead and finish drawing my other trapezoids. You can do the same. Okay, so I'm back. I drew all my trapezoids. Here they are. One of the things that I do want you to notice is that when the function is concave down, these trapezoids are going to be an underestimate. And when the function is concave up, you can see how these trapezoids are now going to be an overestimate. So it just depends on what the concavity of the function is. A concave down, of course, under, concave up, overestimate. Okay. The other thing I want to say is that the difference between the x's, which we call delta x, is really going to be the height of the trapezoid. So you got to keep that in mind. So we're going to get started using this formula, area of a trapezoid. Keep in mind that instead of h, we are going to have 1/2 delta x, and instead of b's, we're going to be using the y's. Okay, so in the case of the first trapezoid, it would be, and looking now that I should put a 1 here, not a 0. Should be y sub 0 plus y sub 1, and so on. Alright, so the area under the curve is going to be approximated by 1/2, this is the first trapezoid, times delta x times y sub 0 plus y sub 1 plus the second trapezoid then would be 1/2 delta x, and this time it's going to be the first base, which is y sub 0, plus the second base, which is y sub 1, plus the second base, y sub 2. And we're just going to keep that going. The next trapezoid, the third one, would be 1/2 delta x times y sub 2 plus y sub 3. And we can keep going until we get n number of trapezoids. In this case, we have exactly 4. But really, it just keeps going. Okay, so I'm just going to put dot, dot, dot. So now the thing that I want you to notice is that all of these trapezoids have something in common. They each have the 1/2 delta x. All of them have the same exact thing. 1/2 delta x, 1/2 delta x. And so what we're going to do with that is we're going to go ahead and try to make this a little more simple. We're going to factor that 1/2 delta x out. So we're now at area, it's approximately 1/2 delta x. And I'm going to use brackets to show that I've taken every 1/2 delta x has been taken out of every single term. And what that leaves you with is y sub 0 plus y sub 1 plus, on this term, y sub 1 plus y sub 2 plus y sub 2 plus y sub 3 plus dot, 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 keeps going. And we're going to go ahead and say that if we drew n number of rectangles, the one right before would be y sub n minus 1 plus y sub n. Okay. So we've taken out the 1/2 delta x, but now let's look in the brackets. There's an interesting pattern here. We start with the first one, y sub 0, which represents that first base, that first wall right here. But after that, we have y sub 1 plus y sub 1. Well, these are exactly the same. So instead of writing y sub 1 plus y sub 1, we could just write that as 2 times y sub 1. But you're going to also notice that that's happening with the y sub 2's. There's 2 of them. And the y sub 3's would happen the same, and the y sub 4's, and it would keep going and going and going. Because what's really happening here is this first base is only utilized by the first trapezoid. But the second base is going to be used for the area of the first trapezoid, and it's going to be used for the area of the second trapezoid. Same thing's going to happen on the next trapezoid. This base is going to be used for the second and the third, and then this base is going to be used for the third and the fourth, and so on and so forth. So what you're going to notice is that the bases that are in the inside are always going to be used twice, while the first and the last are only going to be used once. So what we can do is go ahead and simplify the formula even more. We can say that the area is going to be approximated by 1/2 delta x The first base only gets used once, so we only have it by itself. But the next bases get used twice. So we can just write that as 2y sub 1 plus 2y sub 3 plus 2y sub 4. And so on and so forth. plus 2y sub n minus 1, meaning the trapezoid right before, or the y value of the trapezoid that's right before the last one. But the last one only gets used once. And again, I will repeat that. The inside bases get used twice, one for the trapezoid to the left and one for the trapezoid to the right of it. But the outside bases only really get used once. And so when you come to your formula, you see that represented here. This is the outside base, this is the left side base, the right side base, and everything in the middle gets used twice. And so here is the trapezoid rule. It says that to approximate the area under the curve, you simply take 1/2 times delta x, and I should probably repeat that delta x is b minus a all over n. That's still the same. But when you get ready, inside you're going to take the first y value and add to it the next one, but you got to multiply them by 2. And you do that to every single inside y value, but the outside one is single. It doesn't get multiplied by 2. And so there it is, the trapezoid rule. Area equals 1/2 delta x times y sub 0 plus 2y sub 1 plus 2y sub 2 plus, and I'm just going to shorten it here, 2y sub n minus 1 plus y sub n. And there it is, trapezoid rule. Okay? So this is sort of the proof and how we derive that. If you can remember this formula, then we're going to utilize it in some examples. So it says use 4 trapezoids of equal height to estimate the integral from 1 to 3 of x squared dx. So if you recall, the integral simply means the area under the curve, and we're going to go from 1 to 3, x squared dx. So in this case, I'm not going to necessarily draw a picture, I don't need to, but I am going to keep in mind that n is going to be 4. The number of trapezoids is 4. So I'm going to need 4 trapezoids, and I'm going to try to use that formula that I came up with earlier. So delta x is going to be 3 minus 1, the difference in the interval, and I'm going to divide that by 4. So I come up with 1/2. Okay? So my area is going to be given approximately by 1/2 times the height, which in this case is going to be, or delta x, excuse me, 1/2. And then inside the brackets, I'm going to have the first y value. Well, I got to find some y values. If you think about it, we are going from 1 to 3. So if we're going from 1 to 3, and we are increasing by 1/2, the first y value, y sub naught, the first one, y sub 0, is going to be given by 1. But the next one is going to be given 1/2 later. Whoops, 1, that's a 1. 1/2 later, because that's what we're increasing. That's our delta x. So half a unit later is 1.5. The next y, y sub 2, is going to be given by the next y, which is, in this case, by the next x, sorry, which is 2. And okay, let me fix something here that's important for you to know. The y is not 1. The y is given by when you plug in the x into the function, excuse me. So the x squared is what's going to give you the y, but the x values are going to be determined by that delta x. So I should really repeat that y sub naught, it's not 1, it should be f of 1. Y sub 1 is going to be given by f of 1.5. Y sub 2 then is going to be given by f of 2. And 3 will be given by f of 2.5. Y sub 4 would be given by f of 3. Okay, so again, we're increasing our x's by a half because that's our delta x. And then the y values come from the actual function, okay? And the function's pretty basic, x squared. So our formula says take 1/2, multiply it by the height, in this case delta x is 1/2. And the first y value is going to be f of 1. F of 1 is just 1, 1 squared is 1. Plus 2, remember the formula, you have all of the bases inside get multiplied by 2. So it's going to be 2 times 1.5 squared. Plus 2 times 2 squared. Okay. Plus 2 times 2.5 squared. And then the very last y value, which in this case is 3, only gets multiplied by, it doesn't get multiplied by 2. So you only plug it into the function, which in this case would give you 3 squared. I'll just go ahead and write it as 3 squared. Remember that 1 was also squared when you plugged it in. Once you're done with that, so if you simplify all of this using a calculator, you will get that the area is approximately 8.75. I want to remind you, the x values are, you start them in the interval 1 to 3. That's how we know the interval goes from 1 to 3. The function we're using is x squared. The first y value comes from plugging in the first x value, which is 1. The next x value is 1.5. We plug that in. Then 2 squared, 2.5 squared, and 3 squared. The first y value does not get multiplied by 2. Everything in the middle does, and the last one does not. So you simplify all of that, and that comes out to 8.75. And that's how you use a trapezoid rule using a function. Here's an example that's graphical. It says the area of the shaded region is given by the integral from -2 to 6. So we're going from -2 all the way to 6. Its value can be approximated using trapezoids. Which of the following expression equals the sum of the areas of the trapezoids in the diagram? So go ahead and take a moment and just try to pick one of the answers, multiple choice problem, and then compare with what I come up with. So the answer that I'm going to come up with is letter, or it's not really a letter, but this one right here. And the reason I chose this answer is because if I start with the formula, have 1/2 times the delta x. Well, in this case, if you notice, these trapezoids are all equally spaced 2 units apart. So this is going to be your height right here. And so if I multiply 1/2 times 2, automatically that's going to become 1. And then I just got to keep in mind that inside the first y value is given by -2, f of -2 right here. And we didn't actually have to find it, we just have to know that's where it comes from. But that's only multiplied by 1. Every other y value in the middle, f of 0, f of 2, f of 3, they get multiplied by 2, which is exactly what's happening here. And then the very last one, f of 6, only gets multiplied by 1. So you can see why I chose that one. Now a table example, and this is the one that I gave you in class. If you notice here in this example, I already fixed it, and you need to fix yours. It says use a trapezoidal sum to approximate 0 to 6. Yours says 8. Make sure you change that to a 6. Of t of x dx using 6 trapezoids. So just going back to the table, the temperature is taken in a 6-hour interval. Below is a table of the given temperature. So this is time, and this is the temperature. And what they want you to do is to approximate the area under the curve of t of x using 6 trapezoids, and they gave you a table of values. So just so we understand, x is your independent variable, so this is what's going to give you that delta x. And if you notice, the difference of each x given is always going to be 1. So you can tell that delta x from the get-go is going to be 1. So that's pretty cool. That'll be easy. And then once you come here, you need to realize this is your y sub 0. This is your y sub 1, y sub 2, y sub 3, y sub 4, y sub 5, and y sub 6. So when we're using that formula for the trapezoidal rule, the first one does not get multiplied by 2, and the last one does not get multiplied by 2. Everything in the middle does. So my area is going to equal 1/2 the height, and the height is delta x, and delta x in this case is 1, times the first y value, which is 6.3, plus each of the ones in the middle all get multiplied by 2. So it's going to be 2 times 6.5 plus, and I'm going to pause, finish writing, and you can do the same. Okay, so I kind of ran out of space, but so the area is 1/2 times 1, 6.3, and then everything in the middle gets multiplied by 2, but the last one doesn't. So you can see that here. And so if you simplify that with a calculator, in the end, I get 39.75. 39.75, that's what I get. So hopefully your answer and mine match. Okay, now we're going to look at a second example. The second example says a metal wire of length 8 centimeters is heated at one end. The table above gives selected values of temperature T of x in degrees Celsius of the wire in centimeters from the heated end. The function T is decreasing and twice differentiable. So just to give you a little bit of context, if you have a metal wire and you heat it up on one end, it gets hot, it transfers heat, but as you go away from the source of heat, it's not as hot. And so what they're doing is they're measuring the distance from the source of heat, and they're giving you the temperature at each measurement. And so it makes sense that the temperature is decreasing, and twice differentiable just means that the function is able to have the derivative twice, but it doesn't mean anything for you to take the derivative or anything like that. Alright, so let's get started. And this example is not like the one before, and I want you to really pay attention to this. Our job is to find the integral from 0 to 8 of t of x using trapezoidal sum with, again, this is going to be 4 subintervals. Please don't think that it's always 4 or always 5, it just depends on what they're asking. And sometimes they will ask you for less subintervals than the information given, so you have to make sure you calculate what the delta x is based on that. But in this case they want 4, and since they gave me the data that they gave me with the data that they gave me, the only way to do that is go from 0 to 1, 1 to 5, 1 to 6, and 6 to 8. So here's what's going to happen with this problem. You have to be very careful because the difference of 0 to 1 is only 1, but the difference between 1 and 5 now is 4, and 5 and 6 is 1 again, and 6 and 8 is 2. So you might ask yourself, well, what do I use for delta x? Well, here's the thing. When a problem is given to you in the way that the x's are not changing in the same amount, the difference is not the same, the trapezoid rule cannot apply. So in the previous example, when they gave you the information and they asked us for six trapezoids, you could see that each trapezoid was going to have the same exact delta x. So the trapezoid rule is sort of your shortcut to getting the answer done, or getting the problem done. But when the x's are not the same distance from each other, then you have to throw the trapezoid rule out the door. You cannot use it. It cannot be used. You can't. Now, we're still being asked to do this with trapezoids. We're just not going to use a rule. We're going to just do this one by one. So essentially what we're going to do is we're going to find the area of this trapezoid using the trapezoid area formula. And then we're going to do the same thing for the second, the third, and the fourth. So we essentially have to do these one by one instead of using that shortcut formula. So the area of the trapezoid is simply going to be given by 1/2 the height, which is delta x, and adding the bases. And remember, the bases are your y's. So I'm just going to put y sub 0 plus y sub 1. But depending on which trapezoid we're talking about, those are going to change. Those y values are given right here. These are your y's. So you think this is my first y, second y, third y, fourth y, fifth y. but I'm going to think of these as individual trapezoids and I'm going to add them together in the end. So I guess the best way to approximate this integral is going to be to say, all right, the integral from 0 to 8 of t of x is approximately, okay, now I'm going to go over here and think of trapezoid 1. So I'm going to think t1. All right, my first trapezoid is going to be 1/2 times the delta x. Well, the delta x, I already computed that. That's just 1. And I'm going to add the bases, and the bases are those y values. So I'm just going to do 100 plus 93. Okay. And I think I get 93 over 2, 193 over 2. So I'll compute that with the calculator here in a little bit. Let me go ahead and set up trapezoid 2, because the setup is the most important. I know you can use a calculator. The setup is the one that I want to make sure you get. So for trapezoid 2, the difference between 1 and 5 is 4. So I'm going to have 1/2 times 4. Okay, and then I have to add up the bases, which of course are the y values, so that's 93 plus 70. And then I'm going to have to do the third trapezoid. And the third trapezoid goes from 5 to 6, so we're back to 1 is my delta x. But this time it's 70 plus 62. And then trapezoid 4, it's going to be from 6 to 8, so it's 1/2 times 2. And I'm adding the bases, which is 62 plus 5. Again, remember, imagine that the function was drawn and you had these y values. The delta x would be given by the difference in x's, and the bases would become those y values that you see here. But we cannot use a formula because the width of those trapezoids, the heights, the delta x's, they're not the same. So we have to do it one by one. And when you take an AP test and they give you a problem like this, you have to be very careful that you understand, hey, is this going to be one where I can use the rule or one where I cannot? And this is one where you cannot. So I'm going to pause this and get my calculator out, figure all these out, and add them together. And you can do the same. So I came up with my sums, 96.5, 326, 66, 127, and if I total those, that is 615. So my integral from 0 to 8 of t of x is going to be 615.5 approximately. That's my answer. Hopefully you came up with the same. So that's the lesson on trapezoid rule and trapezoid rectangle approximation method. Here's the official rule. Okay, and keep in mind that it cannot always be used when given a table. You only can use it if the difference in the x's are always the same. But if the difference in the x's varies, then you need to find the area of each trapezoid individually, total it, and get an answer. So now it's your turn. This is your assignments out of your textbook. The first few problems, I believe 1 through 6 are function problems, so they're going to be much like my first example. Then you have 2 tables, and then these are also tables, but it's going to require conversions. Keep in mind, when the units are not the same, you have to do a little conversion. Okay, I'll take your questions on Monday. Hope you're able to understand the objective for the day.